Okay, so we've got a pressure vessel here. The pressure vessel has a mass of 125 kilograms in the cylindrical section, and the end caps are 25 kilograms each. It's got a support, pair of supports here. That's 5 meters each. And then there's basically a bit of an overhang of 1 meter each on either side until you get to where the caps are applied. Uh, Diameter 300 millimeters. Thickness of the pressure vessel wall is 2.5 millimeters. So we want to be treating so we're going to treat the end caps as a point load, basically. And then trying to find the stress state at the point with the highest bending stress if the pressure is 1 megapascal inside the pressure vessel. So overall, just kind of translating these these masses into weight, actual newtons, multiplying by G. So the cylinder, the 125 kilograms, its weight is 1226 newtons. The caps are 245 newtons each. So that gives us a total weight of 1,716 newtons, which means that our reactions at the supports are going to be half that, 858 newtons. I mean, and we can just tell that because it's symmetrical. We don't need to do much more analysis beyond that. By inspection, we know that it's going to be symmetrical there. So the distribution of the weight in the cylinder. So just taking the weight at the cylinder, the 1226 newtons, dividing it by the 7 meter span of the overall length of the cylinder. That gives us 175 newtons per meter. So here's our free body diagram here. Obviously, the x component of the reaction there is going to be 0 because there's nothing else pushing on it. So we have the weight of the caps on either end, and we got this uniform distributed load, the 125 newtons per meter in the middle here, and then the two supports. So we can go from there, and we can draw our shear diagram. So again, weight of the caps pushing down. That's going to be a negative. That's going to start us off with a negative 245 newtons, and then we slant down at a rate of 175 newtons per meter for this 1 meter span. That brings us down to negative 420 newtons. And we get to our support, and we jump up. The amount we jump up is equal to the 858 newtons. So that brings us up to a positive shear of 438 newtons. And then from there, we slant down again at a rate of 175 newtons per meter. Negative 175 newtons per meter, which brings us back down to negative 438 newtons. And then we jump back up again, and that brings us back up to, shocking, the same value that we were down here. So it is a 420 newtons up here, and then we slant back down, and then we get to our 245 newtons. And then, obviously once we apply that load, jump back down to 0. So, based upon our shear diagram, we can figure out what the change of the moments are. So from 0 to 1, it's just going to be based upon the area here. So the area there is going to be 1 meter times negative 245 newtons plus the negative 420 plus the 245. So basically just, this distance here times 1 meter divided by 2 because it's a triangle. So that gives us 332.5 newton meters. So that's from there to there. So we are slanting downwards. There's a slight curve to it. The slope here is less than the slope here, so it's increasing, but it's not one of those ones where the slope's 0 at one end and increases, and it certainly doesn't increase all the way to like infinity. So it's more of a gradual curve. Anyways, so we got that, and then we have the change in the moment from 1 meter to the midspan, 3.5 meters. So again, that'll be just based upon the area of this triangle here. So its base is 2.5 meters. The height there is 438 newtons. So 438 times 2.5, and then just divide by 2 because it's a triangle. That gives us a 537.5 newton meters. So that'll be the increase from here to here. So, and again, based upon the shape of this, we know that the slope is the maximum over here, and then it starts to decrease, decrease until it hits 0 at the top here. So it increases fast and then then levels off. Then as for the rest of the moment diagram, well, we know based upon just the shape here, it's mirrored. This change is equal to this change except negative. This change is equal to this change except negative. So we can just mirror our diagram about this axis and draw it in. We don't need to go ahead and calculate what the difference from here to here is, because it's going to be the same thing as what we calculated right here. So based upon that, we know that the maximum stress caused by the bending moment is going to occur where the magnitude of the bending moment is the highest, so right at the supports. It's not at the middle, because bending moment's higher here than it is here. Or the magnitude's higher here than it is here. And since the bending moment is negative at those points, we know that means that it's curving down like this. So the tension is going to be at the top. And we're worried about where the tension is the highest, because that basically is what, because when we add pressure to this thing, it causes tensile stresses in our hoop and in our tensile hoop stresses and tensile longitudinal stresses. So those are going to add together with the tensile stress induced by the bending moment, as opposed to at the bottom there's a compressive bending stress induced, and that helps cancel out. So we're not worried about that case. We're worried about where things get worse. So yeah, that's at the top of the tank. So again, our bending stress formula, negative my over I. So we need to know what I is. So again, just simple enough. It's pi over 4 times our outer radius to the fourth minus our inner radius to the fourth. So again, a 300 millimeter diameter pressure vessel has a outer radius of 150 millimeters, and then subtract the thickness of 2.5 millimeters from that. That gives us 147.5 millimeters. So yeah, square. Take that to the fourth minus that to the fourth. Gives us 25.8 times 10 to the 6 millimeters to the fourth. So plug in everything in here. Again, just like I like to do, I convert stuff to millimeters. So we got our 332.5 Newton meters times 1,000 millimeters per meter times our y. So y is going to be a positive positive 150 millimeters. Oh yeah, we got two minus signs here that cancel out, the one from here and the fact that the moment's negative, so those cancel out, and divide by our I that we just calculated, ends up giving us, once we cancel out all units, and we end up getting newtons per millimeter squared, which is MPa. Cancel everything, it gives us newtons per millimeter squared. Once we divide by our I, ends up giving us a maximum bending stress induced of 1.93 megapascals. So that's the bending stress. Now, what do we get induced due to the pressure? So our hoop stress formula is just the internal pressure times the radius divided by the thickness. It's assuming that we're working with a thin-walled pressure vessel, which, is going to be a reasonable approximation here. It's, the radius to thickness ratio is 60 to 1, so that's certainly high enough to be considered thin-walled. So with the pressure of 1 megapascal on the inside, that gives us a hoop stress of 60 megapascals and a longitudinal stress of 30 megapascals. And shear stress, so at the top of the cylinder, our shear stress is 0. This is why when we're doing bending calculations and trying to figure out where the bending stress is the worst, we typically ignore what the shear stress is, because the shear stress is always going to be 0 at the top, because the shear flow is 0 at the top. So the shear flow is 0 at the top, shear stress is 0 at the top, but the top is where our maximum, or the top or the bottom, works for both of them. For either of those cases, that's where our bending stresses is the highest. So our highest bending stresses occur at the spot where shear stress is the lowest. It's 0 where the bending stress is the most critical. So shear stress is 0 there. So again, just based upon the coordinate systems we defined at the beginning, our stress in the x direction is equal to the combination of the bending stress and the longitudinal, so that'll be 30.9 MPa. We're not going to have any through thickness stresses induced, so that'll be 0. And then we have our what am I trying to say here? We've got our hoop stress here. Our hoop stress is going to be the stress in the z direction. Oh, actually, I forgot to define my coordinate system, didn't I? Bad me. So coordinate system x, y, z. Same damn coordinate system I always use. So that'll be 60 MPa. So our stress state's going to be this at the point where the bending stress is the highest. So that'll be located right here and right here on the top of the tank, immediately above the supports. And yeah, that's about that.